This is the second in a series of talks on how to build stuff that involves firmware and electronics and mechanics using cheap or free tools. And Dale's going to present most of this, and he's presenting the electronics and firmware part of it, how to connect electronics to firmware, and do both of them. Not necessarily the tools part so much, but more conceptual. And before we started, we wanted to share some robots that are built on the ATtiny, because this talk series is really sort of built around the ATtiny microcontroller as a vehicle for building things that involve firmware and electronics and mechanics. It's not, I mean, it doesn't have to be a robot, it could be anything you want, but we're a robot club, so that's what we chose. And so this is the design as it currently exists, and it just has some IR sensors and backs away when it sees a cliff, so it's basically just a cliff avoider. Looks very nicely done. So there's four of us building this. We've been building it on Tuesday evenings, and I think most of us to a point where we're about to turn the electronics on, or have just turned the electronics on. And so that's like an example. And then Dale built a kind of a very similar thing, slightly different firmware, different mechanics.
Power switch is on the bottom.
I'll let you demo it. And
it's on the battery box, isn't it?
So I guess I'll just finish off by saying that the topics we're going to go over, the Tiny Wanderer show and tell, and what that, how you need to think about requirements when you're doing a project that involves firmware and electronics, a block diagram, a schematic, and how you connect the schematic to code, tool chains, and what's involved in building firmware specifically for the ATtiny or ATmega family, an overview of the peripherals, and then some more software techniques for building in these embedded environments, ending up with, I'll do a little segment on state machines, which are a very handy technique in embedded computing. So, thank you, Dale.
Oh, thank you, Paul. As Paul said, my name is Dale Wheat. I'm going to be giving you a relatively short presentation as a follow-up to the presentation that was given last month. This is really a derivative of a class, an actual lab class that I gave in January on the that I call very tiny development, how to write very simple programs and put them into a very small microcontroller for using low-cost or free tools.
A very good class.
Thank you. Ralph attended that, and we had several people participate in that. And this is kind of a natural outgrowth of that. This is my version of exactly the same robot. It uses the exact same controller card, uses modified hobby servos, smaller wheels, and an overall smaller chassis, with a programming cable still attached, because it gives it the flare.
Is that what you call it?
It's flare, yeah, or a tail. I don't know what you call it. Just laziness. So that is the model of the Tiny Wanderer that was first brought to the club, and there's been several copies of it have been made, and people are working with it. And it's going to continue to evolve and grow over time. People are going to find more improvements, more things you can do with it. One of the first things you'll notice is that some of the parts are made out of fiberboard, and some of the parts are made out of clear plastic. It was originally all clear plastic, very impressive, very space age, until it took a nosedive off the table. Did not survive. Tried to patch it up, that was even less successful. Went with a more durable material, which we can also cut here on the laser cutter. So this is all very producible, to the club project, and I think it has a lot of merit. We're going to show you somehow how the internal workings work, kind of dispel some of the mystery and give you the tools to do a lot of this stuff yourself. So like I said, it's called the Tiny Wanderer. I believe Paul coined that name. After we talked about several different types of demonstration bots, I thought it would be just good to have a little robot that just didn't go off the end of the table. We'll talk about requirements and why it's important to define your requirements, and then he's already covered all this. This is what we're going to do. So let's proceed. You got to define the goal.
You gonna demo that thing?
Eventually.
Okay. This doesn't run.
Yeah, it's a demo. Yeah, it's a presentation, not a hands-on lab. More of a lecture.
Sorry.
No, it goes, but it's not nearly as elegant as that. Would you like a demo now?
Yes, please.
All right. Well, I still
So
have
the
your
goal
attention.
building up to, yeah.
Yes. Okay. And right now it is backing up because it's very scared. Here in a minute, because of the interesting adjustment paradigm that we have. And sometimes it just wakes up scared, wakes up screaming from a nightmare, and it just never
recovers.
Never recovers. I don't know.
So progress isn't always forward. Sometimes you
Room
take a
for
step back.
improvement is what we call this. This is room for improvement, which
So what needs to be closer to the table? Are there any sensors on the other side?
no, no.
For-
It's going
for
backwards. It's
backing
backing up from the what it perceives as the edge.
Because it's an because it's the 8-pin
There we
chip,
go.
we're out of
That was-
pins to put sensors on without using reset.
Not
Line.
necessarily.
I bet there's a bug in there. I bet
No.
there's an initialization bug.
There very well could be, because now it's in the proper mode, and I have no idea what changed.
That happened before.
And you see what
Yes,
it's
it did.
doing? Yeah, it did this exact same thing earlier. Maybe it has to warm up. Maybe the tubes have to get to the, you know,
Yeah,
the
glow right.
The grid temperature has to be up to, and it's kind of sensitive now to the distance and things like that. That can all be fixed in both with improved hardware, for example, a rigid sensor array versus a very bouncy flipping around sensor array, and also more sophisticated software, which we'll get into. And see, it just detects that, backs up, turns a little bit, and continues on. Now, you saw that robot drive in a straight line using two servos that were mounted opposite of each other. This is the same thing, but because I'm using a different algorithm to drive the servos, not as good, without the same kind of resolution, they don't go the same speed, so the robot doesn't go in a straight line. One's going forwards, one's going backwards, as far as it's concerned. But let's talk about, so that's a little demo. It's, as you can see, it sees the edge of the table when it works. And see, now, if you just put it in the center of the table, then it never falls off the table because it goes in a little spiral. That's one solution. Yes,
It's not mapping at all, right?
no, it has no memory of the world. It has no. That sensor probably needs to be just a little farther over.
Oops. Okay.
Anyway, handler error. Okay. Here we are back. It's all scared again. You scared it. Okay, so you get the idea. It does have a basic behavior, and it should run around the edge of the table. I think a robot like this, slightly improved, will be very good for when we do go to functions where we have a booth and we're wanting to demonstrate without bringing a lot of sophisticated equipment out or a lot of complicated demonstrations, which we can do, but this is very easy and it gets a lot of attention. So why do you need good project requirements up front? So you know when to stop. You know when you're done. You can say, I've accomplished what I wanted to do. Here are the requirements that, from my point of view, we wanted to state for this project. It needed to be easy to build, okay, or it wouldn't get built. It needed to be relatively low cost, and I mean not a lot, way under $100, from start to finish. Moves under its own power, but doesn't fall off the table. Because it's easy to build a robot that goes. We've all made robots that go, okay, but get it to stop going. That's the trick. And get it to stop going intelligently. Stop when you need to stop and then go. And then also, to further satisfy my 3 laws of robotics, not only does it move, it needs to blink, and it needs to beep. Okay? So far, this one does not fulfill 3 laws, 3 requirements that I have to make it a robot. However, we're working on that. It is actually blinking right now. Unfortunately, it's in infrared. You can't see it right now. It is blinking, and it only makes two kinds of beeps. One of them sounds like this, and the other one sounds like this. I haven't heard anything. It's making noise. You just can't hear it.
It's the motor's running.
It's the motor's running. Okay. Those are the noises that it makes. So that'd be a technicality. It might scoot by with that. Okay. Yeah. So it definitely needs, but there's no reason we can't have LEDs on every output and input so that you see what's going on. That, of course, LEDs don't cost much, and they are also very helpful in debugging, what is going on. I can't see the infrared light, but it'd be nice if I could have a little LED that came on and went off that followed the output and showed me what it's seeing, rather than getting my camera out and trying to look at it. So we'll add on to it. Like I said, it's an evolving project. Here is my block diagram. Inputs, a controller, you supply power to it, and you have outputs. Okay, and it helps to start at that simple a level. Inputs. Let's talk about what we're using here. We're using infrared proximity sensors. Where's my color? That's supposed to be highlighted. Okay. Is this a PDF?
No.
Or, oh, okay.
Help one?
Never mind. Detecting objects at a distance is tricky. Every method that